Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thank you very much, and thank you for inviting me to give this occasion to speak about this method. This method turned out not to be a method only for programming languages, but it all started there. So let's see. This is how the method evolved. It started in discussions with Yuri Gurevich on when we were logicians, but had to teach courses in programming languages in computer science departments. What's wrong when we teach our students what the meaning of a Pascal program is by using what at the time was the most widespread way of defining these things, denotation and semantics, but when the program runs, maybe it does something different from what we promised. And so Yuri defined this as what he called, we have to sharpen Turing thesis by, and this is a quote, by an alternative computation model which explicitly recognizes finiteness of computers. Now, eventually it turned out finiteness was not really the most important concern here, but this way it all started. So question was, what is an appropriate definition to sharpen this thesis in the sense that if you come with a system, we will be able to come up with an abstract machine which simulates your system in a faithful way and lockstep, as Yuri said at the time. Namely, if your system does one step, then your simulation should do, say, 3 steps or 4. So some constant factor is allowed, but not an arbitrary number of steps. So preventing encoding which you need when you speak about Turing machine. I mean, think about Windows simulated by Turing machine. We all learn to believe that in principle it can be done, but what does it really mean? You can do it only through some encoding which is somehow impractical and maybe of mathematical interest, but certainly not of practical interest. So the question was, what's a good definition of ASM? Took a long time, as a matter of fact, as you see from the figures, essentially 10 years to come up with a definition which became stable. And on the road, we tried with various examples, and at the end of the 80s, I somehow saw that there is practical potential for the notion. And this was by accident that I happened to see this, and it turned out that 2 more things are necessary here. The notion of what I like to call ground models, and I will explain in more detail later on what this means, and a notion of refinement, which is more general than what was there at the time in the literature. Why? To bridge a gap between the ground model, which somehow is like a blueprint of what you want to build, and the implementation, which does hopefully achieve your goal. So essentially what we did at the time was experimenting with various definitions, proposals of definitions for ASMs to see what happens. Can we do this? So we obviously started with simple things like stack machines and Pascal programs and so on, but okay, I will tell you more about this later. And then when I realized that, and this came essentially through dealing with ASMs in the context of logic programming, which you will see on the next slide. I wondered whether this really has to do only with programming language or whether the thesis, Turing thesis in a generalized form, should apply to more than just language semantics. So that's how I tried to find areas where trying to model with ASMs and to verify properties of these machines would fail. And it never failed, which I took as sort of confirmation of the thesis. It's a pragmatic confirmation of the thesis. And it led to the final definition of what an abstract state machine is, what I will give you in a couple of minutes. It's in the so-called Lipari Guide, written by Yuri Koryevich. Lipari Guide, because he presented this at a summer school which I organized in Lipari, and this definition came out in '95. Now, since then, the major concern was how to integrate this method into more general software development environments. So that's the evolution of the method. Some people claim that it died, but that's a wrong claim, you will see. So I will have to speak about three things: definition of ASM, what a ground model is, and what ASM refinement, differently from usual notions of refinement in the literature, is. So these three things, I want to speak about them shortly. Now, as an afterthought, it's easy to explain what an ASM is. You all know it. You all know finite state machines. Look, a finite state machine changes given an input, controlled state, or internal state, as it is usually called in the literature, and maybe gives some output using two functions, delta and lambda, which you all know what they are. So what are the characteristic restrictions here? You have only three locations: one for input, the controlled state, so the internal state of the machine, and an output location where the machine prints something. There are no shared locations. So it's a mono-agent view, and as such, it was okay, but that's a restriction. You have strict separation of input and output. They can never be mixed. Then you see there are only two simultaneous updates, because this machine simultaneously does two things: control state update and output update. You never thought about this probably, but somehow that happens in parallel. Or you can think about it as happening in parallel. It doesn't mean anything to say that this is somehow sequentially ordered. But there are only two such simultaneous updates. Then you have very special data types. So what is input? Usually it's words or letters. What is output? Same. What are control states? Just labels or numbers. So very special data types, which can sit in these locations. And next restriction, you see these two functions, delta and lambda. They are what I call background function. There are only two of them. They are static. They are defined by the program. Now, why these restrictions? If we want to prove a general thesis, we need more. So try to take away all these restrictions, and then you have what an ASM is. Namely, you allow arbitrarily many simultaneous updates in one step, not just two. You allow arbitrarily many locations, not just two. You allow them to be parameterized, so they are sort of array variables of programming. And you allow them to be shared in the sense of that there may be multiple agents which may read and write. And if they do on the same location at the same time, you need a protocol to guarantee some kind of consistency. Then allow arbitrary data structures, which means values of arbitrary type sitting in your locations. So why should it be a number or a label? Why not a word? Why not a train? Why not any object of your application domain? Then also the background where you are working. We saw it in Grigory's talk. You may have a very complicated background. Why just two functions, delta and lambda? No, you may have arbitrary background, which somehow you know as an application domain expert, and you're building on top of this. And that means, if you take this view, that the conditions in these rules, if you remember the interpreter for finite state machine, it depends on input being defined. So when there is an input, then the machine does a step. Now, if you have arbitrary data structures as your environment, then you may have arbitrary conditions instead of just input being defined. And this is the final definition of abstract state machine Yuri gave in the Lipari Guide. It's a set of rules, finite set of rules of that form, if conditions and updates, where updates are, as you see here, assignments, but with arbitrary terms, T1, Tn, and T, and arbitrary function symbols, F. And conditions correspondingly are arbitrary conditions in your language. Usually we use first order theory, maybe enriched by whatever background structures you have to be expressed. Now, what's the meaning of these ASMs? Such a machine in one step, in a given state means configuration of your structures, of your data structures. It will evaluate all the conditions, and for those conditions which happen to be true in this state, it will evaluate all these terms, T1 to Tn and T, produce concrete values, A1 to An and A, and then in one blow will update all these functions, the function interpretation, at the calculated positions, A1 to An, by the new calculated value A, simultaneously. As we did here with simultaneous update of control state and out. You see, this is a calculation of some new value, and this will be assigned as value of those locations. So that's what an ASM does. That's all. Now, what is a ground model? Now, this also is not a new concept, and even in semiconductor industry, it's called golden models, and they know why they call them golden models. They are blueprints. So there are many papers on this, what that could be, and there's a nice paper by the way, very old paper. It's a problem of philosophy or epistemology, if you want to. How to relate some reality you want to describe to your description. How to make sure that your description really conveys the meaning of what you have in your head when you speak about this piece of reality. So that's what Brooke calls the conceptual construct or the essence of a software system. Now, the important point here is that we need such models prior to coding. And close to reality, we want to describe by a software-based system. And this grounding of design in reality, so it must speak about correctness, but this is not mathematical correctness. It's correctness in the sense of correct relation between the concept you have in your model and the underlying reality you want to describe by that concept. It has to be complete in the sense that everything which is semantically relevant, so relevant for the eventually desired behavior of your system, should be in this model, because you should not be allowed to introduce something semantically relevant during the refinement process which leads from that ground model to code, because otherwise your ground model doesn't convey the correct idea on what your system is supposed to do. Now, in the case of programming language, that's what Grigori said before. The programmer should be able to know what a program does without knowing all the details of all the optimizations of the underlying compiler. If you have to know if you have the view that the compiler defines semantics, yeah, that's something which I wouldn't accept. The ground model should be independent of particular compilation procedures. So in that sense, the ground model should be complete. And these two properties, correctness and completeness, I insist on this. These are not things you can handle mathematically. So what can you do if not mathematically? Okay, so skip about that. This is a communication problem because this is more in the software engineering environment. But the verification method problem, you want to show that your model is correct with respect to, let's take the example of Java, to the Java manual. What can you do? You go to the manual, you read the manual, and you compare it with your model. And this comparison should be possible. And it should be such that you can really decide upon the issues which may happen here. So if your model says something different from what the manual says, and typically it will do in certain situations because the manual is probably not complete, maybe ambiguous in certain contexts and so on. So you should be able to run a usual inspection process as you do with code, but this time you have your model and the informal description of what in general people would call a requirement document. And here the validation problem is important, and again I can refer to Grigory's talk. I completely agree that if you do such kind of definition of formal, precise definition of something which you want to take as a contract for coding, you must be able to test it. There must be a possibility to run it. So here are examples. Examples of ground models for programming languages. So these are examples through which I eventually understood the practical potential of ASMs. So it all started with Prolog, and by various accidents, I happened to become a member of the ISO Prolog standardization committee, and we built a model for the ISO standard. It became the official definition of the ISO standard in the sense of its appendix of the standard document. Similar thing happened for hardware design language VHDL in '93. Another outstanding example, I think, is the SDL language from the International Telecommunication Union. And here, again, that ground model, which came in terms of abstract state machines, it became the official standard definition. For C#, we modeled the ECMA standard. So the ECMA standard was there, and we built a model trying to formalize what the standard says and to point out where the standard was not precise enough or ambiguous or inconsistent. Because this is what typically happens when you do such modeling, that you find all these border cases. And other two examples are in the application to business process modeling. So there are two languages, one execution language called Beeple, and another is a recent OMG standard for business process modeling notation. That's how it is called. Other examples are, and I will speak more about this, a basis for verifiably correct refinements of the model to an implementation. And here the examples I want to discuss in more detail. One is Java JVM, and the other is Occam to transputer. This was a case of implementation of parallel constructs of Occam by the sequential execution on the transputer model. And this includes machine verification of various of these attempts to verify. The one I will speak more about is a Prolog to Warren abstract machine combination scheme, which was proved to be correct using the KIF verification system. And PVS has been used in a large project I will mention later on by Groß Langbach and Van Henke, where they used ASMs to describe front and back ends for exhibiting a concrete correct compiler for concrete realistic language and concrete realistic machines on which the compiled code is executed. So, so much for examples, some examples of ground models. And here's why it is important to be able to execute the example. So in the case of Java and JVM, I will show you, we made models of Java, of JVM, of bytecode verifier and a compiler and so on. And these are on the left side, so a model for execution of a Java program at the level at which the programmer looks at the program, a model for the compiler, a model for the JVM, and here you have the real implementation as it was there at the time. And so these three machines are executable. This was done by Joachim Schmidt using defining the background functions in ASM Gopher. And now what you can do, you can mix. You start with a program, you execute it here in our machine, you compile it by Sans compiler and run it here. And now you make comparison whether the results are in the relation which you would expect. But you may now see that something goes wrong. Where is a mistake? Is a mistake here? Is a mistake there? In which model? So what you can do, you compile by this, and using this library function, you transform it to the textual representation here, and now you run our JVM machine. So you can figure out, is a mistake here, is a mistake here. Same thing here, we can compile with our compiler and then run it on the real Sun machine. And going this way, we discovered a lot of incoherences and eventually became sure whether it was our mistake of in this modeling or Sun's mistake in implementing. And we have a lot of, a long list of errors which we have put on Sun's bug parade at the time, and they were all corrected by Sun. So they were all recognized. This is because I'm sorry, because our claim was we wanted to show that this model here, this is a correct ground model reflecting what the manual intends to convey to the programmer, in the sense of that the programmer can rely upon this as behavior of when the program is executed on Sun's machines. Okay, so third notion, the one of refinement. Now here, the difference between what at the time was there in the literature is rather strong in the sense of, first of all, it's based on the operational view, which is suggested by using abstract state machines, which at the time was considered as a sort of sin. So I was very happy to hear Grigory's talk that he somehow showed that this dichotomy, which in the 80s and still 90s was considered as existing between operational and declarative approaches, that's not something real, because whether you have an axiomatic or an operational description, it depends on what you want to do and depends on where you want to go. And certainly there are two phases of one method trying to produce code which you can verify to have certain properties. But at the time, this was considered as a kind of sin, but I saw that this is the right thing to do. So you start from notion of state. With this refinement concept, you are, as a designer, free to define what kind of refinement you want to. So you define what is the refined notion of state, which means refining your locations, your data structures. Then you usually do not want to compare any two states of the abstract and the concrete machine, but only certain states. So you define as a designer what you want to declare as pairs of states of interest, abstract and refined one. Then when you define these states, you usually do not want to speak about any single abstract and every single refined state and compare them somehow, even if of interest. But in between, you may do many computation steps where, so to speak, you do not want to make any comparison because probably it's not even possible, or only at a very high price. So you choose what are the computation segments which lead from one pair of corresponding states of interest to another pair of corresponding states of interest. And then when you compare these states, you typically do not compare entire states, but only certain locations, cells, as Grigor would say. So you have what I call locations of interest and corresponding locations of interest. And then the relation you have between them, often it is an equivalence, but maybe not even an equivalence. It may be any mathematically precise relation. Think about what an assignment means at the programmer view and what it means for the compiler. Compiler does many, many small things to do one assignment step. As a programmer, you think x gets assigned the new value v, which is a value of an expression x, e, which you had there. So compiler does a lot of things for reaching this. And what compiler does, compiler puts this value on some stack, intermediate values, and then eventually stores back to the register. So you have a register assignment to variables in your programmer model. So there are a lot of things you have to care about, but the relation you want to have at the very end, that's very clear, that the value which you see as a programmer sitting in your variable x after the assignment is in the correct relation to the value which will be sitting in the register to which the compiler eventually will have, the execution of the compiled code will have assigned the value. And the values need not to be equivalent, need not to be the same. They are in some relation. You see it even in Java JVM. Java and JVM, they have very similar type structure, but it's not the same. It's in a certain relation which you have to be to be made clear. So you have all this freedom, you as a designer, when you define a refinement step. And then we say a refinement is correct if for each refined run and for each pair of corresponding states happening, you will find a corresponding pair of states, a next corresponding pair of states of interest, where again the desired relation will hold if the system doesn't stop. So if it terminates and you impose properly equivalence condition on the initial and final state, but it may not terminate. So that's a very general concept. As a matter of fact, it turned out that it covers all the concepts of refinement which were there at the time in the literature. And here's the main usage I could make out of this. And yeah, that's a story about logic programming languages where it all started. So we constructed hierarchical levels for the isoprolog model. So the isoprolog model came as a core model with just 4 rules. So it's half a page. It's a core behavior of what this prolog machine really did. And then there were a lot of so-called built-in predicates for all kinds of things you could do, like manipulation of list, of tree, of the so-called built-in predicates. And each of them came with a small set of rules, which you can add. That's what I call piecemeal horizontal extension. Then it turned out that refinement could be used to extend this model, this standard sequential execution model of the ISO standard, into a model for prolog with parallelism. At the time, it was called prolog 3. This was a system by Kolmauer in Marseille. And the only thing you had to change was replace unification, which was the basis of the prolog mechanism, by constraint solving. So you take away the rule for unification, replace it by a set of rules for constraint solving, and all the rest is the same. So you refine this notion of what it means to successfully do to be able to do one basic step because of successful unification or successful satisfaction of constraints. Then another example was introducing polymorphism. There was a machine developed by IBM with a language called Protozerl, and the underlying machine, like the Warren abstract machine. And here the same. You just edit conditions on types, and in the underlying unification algorithm and the underlying rule describing this, you had to add the conditions on the typing. Same thing for a functional extension of prolog. Babel, it was called, made by people in Madrid, or with object orientation and other forms of parallelism which came from England, so Parlog, Concur, Parlog, Pandora. Or even one more example where there was an abstract execution, more abstract execution strategy than in Prolog, in a system called Gödel, developed in Bristol, I think it was. And here again, instead of just speaking about unification, you spoke about this abstract execution strategy. So there were all refinements of this basic isoprolog model, which I defined without knowing all these other languages. So somehow it explains that you can try to listen, so to speak, to the subject, which here was the basic feature of what prolog step does. And then apparently you can refine this to various other forms of the same kind of idea of one step, but with different strategies tailored for either parallelism or typing or more abstract execution strategies. And yes?
So in this case, refinement means that the isoprolog execution was faithfully extended by a corresponding execution in these other languages. So what was exactly, how is this notion of refinement related to this notion more of simulation that you presented before?
Yes, okay. So it means that if here you have the isoprolog and here you have one of these other systems, when this isoprolog thing does, say, a step with unification, in this particular case, here you would, of prolog 3, here you would have a certain number of steps for constraint solving. But you know that at the beginning and end of this unification and constraint solving attempt, you can do the comparison. And you show that the relation is correct. Okay?
So another way to put it is that you showed that all these different languages faithfully included as a sublanguage the isoprolog language, in a sense, right?
In a sense, you could view it that way, but this was not how it went historically. But yes, in a sense, you can say it.
Well, I mean, at a very high level, that's what you're achieving, right?
Okay, let me say yes. There is even, okay, I will give an example where this can be made very concrete. Okay, yeah, so I agree. Other example was vertical refinement. So vertical refinement has to do with the way how you go to implementation, where you add data structures and you also add new roots, because now you do something much more detailed than at the abstract level, but still you have certain points where you make connections to make sure that the implementation step or the design idea for an implementation step is correct. And so here the first example where I learned how you can go was Prolog 2. At the time, the machine which made Prolog efficient was a Warren-Nafzak machine. And we had 13 refinement levels. So later I tried to do it in the parallel context of Occam-to-Transputer, so trying to show that InMOS compilation scheme for compiling Occam programs to the sequential transputer model was correct. And there we had 15 levels. So, and I will explain it for Java and JVM. And a similar thing we could do for C#, the CLR. Now, the point here was we tried to, and I saw that this is possible to reuse justifications, not just reuse your models, but reuse your verification steps as much as possible. So here's the example where I want to confirm what you said. There was a system called constraint logic programming over a given domain R, developed in Yorktown Heights by okay, I forgot the name, but it will come. And there was a corresponding constraint logic arithmetical machine. Now, we reused the Prolog to 1 specification for specifying CLP to clump, and also the proofs. And it turned out that at the very end, and this was what Bayerle did, he made an abstract machine, an abstract Prolog programming machine with constraints, with some X for the kind of constraints which you have, and you can plug in for X any specific structure you want to have, and it all works. So in that sense, it's so to speak, the basic scheme of Prolog, which has many, many of these instantiations, and you can reuse the models, and you can reuse the proofs. Why does it work so nicely here? Because we always took care to develop these extensions as much as possible in a purely incremental manner, as it is said in computer science. And this corresponds to what logicians know as conservative extension of theories. And if you can extend your theories in a conservative way, you can reuse proofs for the theory you're starting with when proving things about the extended theory. And that's a very nice method which has been used and used and used again in this approach. Okay, as you see from this picture, the general case here is to capture orthogonalities of components, and on this I will speak a little bit more now. Here's an example. The horizontal refinements of Java and the JVM. By splitting the language into imperative code, class-related features, object-oriented features, exception handling features, and concurrency features, doing the same with a set of instructions, or something like 180 instructions, which were there at the time in JVM, and also doing the compiler between these levels. So splitting the definition of the entire language into a definition of these sub-languages, where each of the following one conservatively extends the previous one. That's an important point. Then what we also needed to cut down the complexity of the thing is to parameterize, obviously, the kind of instructions, so that you come up with something which one can call instruction-wise design and verification, which corresponds very much to what you proposed. And yeah, please.
Can I ask a question? When you define the imperative sublanguage of Java,
yes,
you define various macros and notation, I think, in your framework as abbreviations, and use those in expressing your rules.
yes.
Do you need to redefine those when, for instance, you introduce threads? Or could you compare it with the modularity that Grigori Rosu achieves with the K framework?
No, we can reuse the same macros. What changes are the instances of, I will give you an example. Here's one. So good questions are those which lead to the next slide. Here it is. So this is the entire machine for evaluation of expressions in the imperative part, where you see for each construct of the language, you will have a set of rules. So you have literals, you have variables, you have unary operators, you have binary operators, you have assignment expressions, and you have conditional expressions. And for each of them, don't read the details. For each of them, you have a group of rules which tells you what happens when the interpreter encounters such a construct and what the interpreter has to do. So the macros Peter is referring to is, for example, what means context of a position. And these things never change because they are essentially only speaking about how the interpreter runs over the syntax tree. So and that thing remains the same in whatever variation of such constructs you would like to introduce. So the important thing is here that you have one rule group per grammar clause. And I will speak about this more because this can be interpreted as a feature-based approach in the more general sense as it is used in software engineering. So for each feature or language construct which you have, you may add a couple of rules, and very much like Grigor said in his talk. Next example, this is the corresponding part for imperative statements. Here again, what do you see? The empty statement, expression statement, break statement, continue statement. There are some rules which deal with how to jump from a break or continue back to where you have to go. Then sequential statements, if then else statements, while statement, and declaration. That's all. So that's what we call the imperative code. And here again, you have one group of rules for each construct in your formal language definition. And the important thing you see is some of the rules, they will trigger the execution of expression evaluation rules, so of the rules of the previous machine. For example, here, when you see an expression, so to execute an expression statement, you certainly first have to evaluate that expression. So you jump on your tree to the position alpha where the subtree for that expression starts, and now this machine stops, but the previous one will go, and it will evaluate the expression, and it will come back with a value like here, a literal or log. If composed with unary or binary operator, it will come back with a value, and you give it to the statement. Okay, so that's how, when we want to verify that an expression statement execution has a certain property, we will rely upon, in the proof, that we have proved already something on what the expression evaluation mechanism did as induction hypothesis. So you see in composing this, we do something which corresponds to what we do in our theorem provers to split the concern into something you can prove by using induction on the structure of your syntax. Okay, now vertical refinement. So vertical refinement. You have seen we have to define the language by some grammar. So we have a parser, which will produce an abstract syntax tree. Then we have the compiler. We have the virtual machine. We have this interpreter run. So our model for executing a program at the level as a programmer sees it. And proof relating these two runs by saying that when the compiled code is executed, it does what the programmer expects here. what has been promised by the ground model or what is written in the manual. So similarly for other components like class loader, like bytecode verifier, preparator, and so on. So here you see the different levels, and that's why I call them vertical refinements, because you have many details to care about what one step in this Java program means when the corresponding bytecode will be executed. So the point here is that these two ways to refine, horizontal and vertical, they are compatible. And that's how, in discussing with Don Battori, we realized that this is very similar to what people did in a feature-based software engineering community. So think about the expression evaluation machine. So here we have a Java interpreter for evaluation of expression. We have the corresponding JVM interpreter for compiled expressions. We have this compiler for Java to JVM for expressions and the corresponding theorem, where the theorem says that when an expression is evaluated here and it is evaluated there on the compiled code, then these two evaluations are related in the right way. That's our correctness theorem. And the theorem is conveniently split into two components, statement and the very proof. Because it turned out that both things can change in a rather complex way. Now, let's try to compose. So I'm saying this is compatible with vertical refinement. Take the corresponding components for statement, imperative statement execution in Java on the JVM with the compiler and the theorem. And it turns out you can do it tuple-wise, component-wise. So you have what Battori calls a tuple representation, and you can do this composition component by component. So you compose a Java interpreter, you compose a JVM interpreter, you compose a compiler, and you compose your theorem and your statement formulation and your proof. Here's one example. So in the case of imperative code, the Java expression evaluation, you have seen it. It had 6 groups of rules, 1 per grammar clause. The statement thing had 9 more rules, and they are orthogonal in the sense of they never can be executed simultaneously, but one can call the other. The statement execution part can call the expression evaluation part, and back from the expression evaluation, you will go to statement execution. So they are linked, but the precise points of interaction are precise. And these are the points where we use induction hypothesis in our proofs. So similar, when we go to the compiler, for Java, for expressions, we have 6 recursive equations, plus 11, which have to do with non-strict evaluation of expressions. By the way, this is the case for ground model instead of accepting compiler as definition of your code. We had some trouble we had first considered a compilation, let's say standard compilation scheme for expressions. And we didn't succeed to carry through the proof for correctness at this level when we were at the level of JVM and bytecode verifier. So something was wrong. Eventually, we understood what was wrong. That the bytecode verifier of Sun at the time, this was documented nowhere, used a very specific evaluation for non-strict evaluation of Boolean expressions. Now, this was not written, so nowhere in the Java manual, nowhere in the JVM manual, but it happened. I think it's wrong. The programmer should know that this is enforced by the bytecode verifier, because otherwise you can write correct programs which your bytecode verifier will not accept, and you don't understand why. Okay, so we have made this explicit by adding these 11 rules for non-strict Boolean expression evaluation. But okay, that's a side remark. Now, the theorem statement, it has 5 invariants. They are about equivalence of values of local variables in the Java code and of the corresponding assigned registers in the JVM. Then about equivalent positions in the sense of when Java does an assignment statement, the JVM will be at the beginning of the compiled code of that statement. And when Java has finished that assignment statement, the JVM will have executed the last instruction of the compiled code for this. Now, this is equivalence of positions, so to speak. Then that the intermediate values which you may have computed, that they correspond to each other. So this is at the beginning and at the end of expression evaluation. And here you need 2 for strict and 2 for non-strict expressions. Now, when you go to statement execution, you need 3 more invariants, because now you need to know what it means to begin and to end a statement execution. So corresponding positions at the beginning of statement execution in the Java and the JVM model. And since a statement may be executed in a normal or an abrupted way, abrupted by go to, by continue, by break, not go to by break or continue, or by exception, or by return, or by calling a procedure. So you have to foresee these 2 cases. So there are 3 more invariants. So in your proof, you will use the proof we had, and now we have to add proof part for these 3 new invariants. And they will use induction hypothesis for corresponding invariants for expression evaluation, because it is used in all these cases. Okay, so if you look at the details, the verification has 13 cases, and we have 22 new cases when dealing with statement execution. And they all come from what can happen to a construct of the Java language or its compilation in the JVM when executed. So there are cases which come, so to speak, from the real code. They do not depend on the proving mechanism. Okay, so much for example. So here's a complete picture. What has, yes, please?
So it's, I don't know if you said this explicitly, but at least implicitly, you're thinking of a proof theoretic verification and not a model theoretic verification.
Proof theoretic, yes.
Okay, because that could be a difference in the way some of these things play out.
Yeah, so I'm speaking about theorem proving.
Yeah.
Okay, so what we have, let me be brief here. So starting from a Java program, we have this interpreter for Java, we have this compiler, we have this JVM, and this JVM, to be able to handle all this, because it's not an easy enterprise to show things like type safety and compiler soundness and bytecode verifier correctness and completeness and so on. So we have split this into what we call a trustful JVM, which is a machine which just executes any code it gets, whether bytecode verified or not. And from looking at this, we defined a defensive version, an idea we took from an ACL2 version of subpart of Java, which has been verified. And so the defensive machine at runtime checks all the conditions which are important for code to be correctly executed. And then we collect this into a notion of bytecode type assignment, and out of this we made a bytecode verifier. Why did we have to do this? Because at the time there was no information on how the bytecode verifier works. Nobody knew. Some didn't give the code, and in the manual it's not described except by examples. So we defined a bytecode verifier, and then we showed that if code comes from here, which is compiled respecting this scheme, so the theorems are sort of schemes, not for concrete compiler, but for compilation function, then it will be accepted by the guidecode verifier, and if it is accepted, then it will be executed here on the trustful machine. And during that execution, none of the conditions which have been checked by the bytecode verifier will ever be violated, and also the behavior is correct with respect to this. Now, the challenge I see here is, let us try to make such a theorem to be not only provable by theorem prover. At the time, I've challenged the various theorem proving communities, written to them, here's a book, here are the proofs, can you do it with your theorem prover? Only one group replied positively, that was the KIF group, the ones who did the prologue to WAM verification. But what I wanted is not only doing the proof supported by machines. But support this stepwise refinement method, because that would give us the chance to reuse and make it scalable for defining variations and new languages. What we did ourselves, so this was a student of Robert Stark, he reused these models for proving the corresponding properties for C# and the underlying virtual machine. Now, this was a project which explicitly started as follows. Take these models and try to show that there are models of C# and .NET CLR. Where impossible, change a model so to make it work, but make it work in such a way that it can be used for both languages, Java, C# and JVM and .CLR. And as an afterthought, it turned out that we could have done, I think, no, I don't have it on this slide. So with Robert Stark, we realized we could have done an abstract version of all these machines, these interpreters for the language and the JVM, with parameters which can be instantiated in one way, and they produce the Java JVM model. In another way, they produce the .NET CLR and C# model, and that's in the paper.
So,
yeah.
How similar are the languages? I mean, are they really, really similar? Or?
Java and C#, yes, they are very similar, but there are certain differences.
I actually would expect to see much more difference at the CLR and JVM levels.
True.
I'm surprised,
Yes, yes.
that that's so easily unified.
Yes, you are right. Yeah, that's true. Yeah, but for example, here, even some of the proofs, I mean, this was part of a PhD thesis, so we didn't force him to do everything. But for example, the exception handling thing. We had a theorem that under certain conditions, exception handling in Java and JVM is correct. And the same theorem worked here, but there was a lot of work to do because of the difference of exception handling in .NET CLR. Yeah, but the interesting thing here is you see the differences. Yeah, so you make them explicit, and you see, here the design decision was to go this way, and that's what the model tells you. So in that sense, I think this has to do with scalability. So a few minutes are left. Let me speak about modeling other systems. So you see, it started with programming languages, and in the 90s, first half of the 90s, we really were always working with programming languages because, I mean, as a logician, what do you know about computer science? You know some language, and that's all you know. But I tried to do more. So modeling the parallel systems, in ASM, there is this synchronous parallelism, which I told you, simultaneous execution of many rules and many updates. Now, that fits very well architecture design. And we experimented this for specific machines built by physicists in Pisa and Rome. It was called ARPE. And they had a long compilation chain bringing this to the microprocessor level. And it could just be done by using ASMs because of this inherent parallelism. Now, another project, we tried to do verification of risk pipelining. And this became an extensive environment for modeling application-specific instruction set processors by a group in Paderborn and now in Erlangen. Here's another example. What about distributed systems, where parallelism is not anymore synchronous but asynchronous? That was the next challenge. Now here, I took the example of Occam, where Yuri had defined a model with Larry Moss when there was not yet the notion which now we call asynchronous or distributed ASM. So it was an attempt to refine ASM in such a way that it fits the parallelism of Occam. Later it turned out this was very specific, can be done in a better way, and this is what the Liberi guide of Yuri's definition gave us. So we started to do this model again for concurrent non-deterministic Occam, and this is a model which we could prove to be stepwise refinable to transmuter code, taking as definition the compilation procedure InMOS suggested for compiling Occam to transmuter code. So in a sense, we showed correctness of this inmost compilation scheme using this Liberi guide notion of asynchronous subset state machine, which fits this view of Occam, and leading to the transputer level, which is purely sequential. Yeah, that is this paper here. Okay, another example, interpreters for domain-specific languages. There's a certain variety. Just let me give you the buzzwords. Here is a language which speaks about scheduling for business processes. And this was a variation of the product ground model, strangely enough. So I was very much surprised when I saw this, but in a sense, this backtracking mechanism gives you something which allows you to speak conveniently about scheduling. Then control for event-driven database applications. Then I mentioned this VHDL language. That's, again, an interesting case for refinement because it has been extended, as you see here, in various ways by various groups, to a pictorial extension, to an analog extension, to an extension to Verilog, and to the more recent system C and Spec C. And it all worked. At Union Bank of Switzerland, Kutter and Thiele, they used models to model driver specification language. A language just for specifying drivers, which were used at Union Bank of Switzerland. And the other example I mentioned before is this SDR 2000 language. One step more, what about business process modeling and web service languages? So one early version was the so-called UML activity diagram. So here we speak about languages which have graphical structure. They come with pictorial representation like diagrams and put semantics on those. And there's a group in Ulm, they used early models we had for UML activity diagram and put this into a development approach for business process design, which gives you the possibility of defining your ground model by using the activity diagram. So assign precise ASM semantics to these diagrams, which you as an application expert use to program your business process. And then the whole rest of the machinery does it for you. It compiles this to executable code and will run your business process. And you are sure that this is correct because it has been shown to be correct. The group in Vancouver, they did this for the Beeple language. And recently we built a model for the BPMN 2.0 standard, essentially to show all the ambiguities and all the undefinabilities which are in the standard. These are really undefinabilities in the sense of the standard has inconsistent and contradictory claims, allowing business process constructs to be implemented this or the other way, which will have the effect, and it has been shown in the literature, that the resulting systems are not compatible, which is exactly the opposite of what the standard should do. Standard should provide that different implementations are compatible and interchangeable, and they are not in this case. So we have used the ASM model to show this explicitly where these things are wrong. The very last example, I have 1 more minute, I guess. This is, I happen to know this approach. It's called subject-oriented business process management. And they wanted, this is a sort of graphical notation which tries to improve about the deficiencies of BPMN, so you don't have to know the details. But they had a problem of conveying the intended interpretation of these constructs to the users. Now, it turned out that we could build an ASM model for this. And here again, on the next 2 slides, next 3 slides, I will show you the model in graphical, finite state machine graphical notation. I don't want you to see the details, but just to see the overall picture of the complexity of this thing, which is a huge tool sold by a company. But the entire semantics is in this. So this is a general picture. It's a kind of iteration. You try to do something, namely to do a communication act which is either sending or receiving. So you try to do this, and you see here there are various ways to end up by timeout, by an interrupt, and so on. And you do your attempt, which may or may not lead to termination. And you use an intermediate abstract machine try alternative for sending or receiving. Now, that machine is defined fully here. This is for sending, and this is for receiving. And you see it's, again, a purely iterative structure, very clear from point of view of programming. And that's all you have to know. So, okay, that's my last example. And here are references if you want to see details. Thank you very much.
Time for a couple of questions.
So maybe a question to both of you. So ASMs have been very actively worked on inside Microsoft. So can you update us a bit on the current status there? What is the...
Gosh, not in Cambridge, unfortunately. I think that's mostly in Redmond. I don't know if anyone else in...
I can tell you more about this. So it has been very active from 2000 to 2004, more or less. And there are two major outcomes. One was definition of what is called the Explorer. It's a debugger mechanism which allows you to compare runs of an executable version of an ASM and runs of code, of C# code, and to compare them. And that has been very successful and is at present used in the Windows production group. So it has been taken out of Microsoft Research and went to Windows production group. But unfortunately, that was the end of the story of ASMs at Microsoft, because Wolfram Schulte thought that other things are more important and more successful, and that ended there, with one exception. When Monty tried to, and eventually find Microsoft for the story you all know, the problem was how to provide information on Microsoft code without giving the code. And what has been done, ASM models have been built and have been sent to Brussels, and this has been accepted. And for Microsoft, that was a lot of money, which was saved by being able to send these. But unfortunately, that's the end of the story at Microsoft. And as a matter of fact, their interpreter was called ASML. It's not supported for many years now, for almost 10 years. Now there is a free version of this because they gave the code to a group in Ulm, the group I mentioned, which did this UML activity diagram-based development environment for business processes. They have the code for ASML, so if you want to run this code, you can get it. I'm very unhappy about this situation because when I helped Yuri in 2000 to build this group, I saw three alternatives. One was, so first of all, I had succeeded to make a proposal from Siemens where we had a prototypical environment for all this at the end of '99 to cooperate. And Siemens was ready to do it, and Microsoft refused. But then I said, okay, one of three things should happen. Either you build a system which we can buy with assistant and everything, or you give it for free. But not what has happened, namely to build this ASML, to give it to academia people without any support, without any help. So it's hanging there, and you don't even eat your own dog food, no? Because you don't even specify your system using ASMs. They didn't. And that's what happened. So the eventual outcome of this was that the system was abandoned. And this is unfortunate, very unfortunate. But okay, that's the end of the story. But there is Core SA. So there's a free version of an interpreter which has been developed in Pisa and in Vancouver. And you can access it through the web. And it's developed now also in Ulm. So there are three groups working on it. And the fourth group in Linz is starting. It's a component-based system with a kernel for Core ASM. And then you can build a lot of plugins around for doing various things. And that's very active. That's for execution mechanisms. Now, for theory improving, I mentioned some examples. So PVS has a certain number of theories which have been used for proving correctness of compilers. Then KIF has been used for similar purposes. Isabelle has been started to be used, but that has finished. And what else? There is a special purpose theory improver by Sterk, which has been used to prove correctness of thread manipulation in the Java model and so on. And then there are various model checkers which have been attached to ASMs. But it's all, these are activities taken up by people who were sitting in, it's not coordinated, except for me trying to bring people together, but okay.
Yeah, as you say, this is very unfortunate, since this is really an impressive body of work which other people cannot not easily access and apply. So maybe some open source activity should be promoted.
It's a tool support which is in a bad state in a sense, no? Because the only good tool which we have is this execution mechanism called ASM. And specialists who were able to do proofs in KIF, in Isabelle, in PVS, but you need specialists for doing this.
I mean, I think product teams do find it hard to take on specification, formal specification, unless they can see real advantages from the point of view of test generation, say, something like that, something concrete. But,
I can tell you even more. I mean, this was when I ended my sabbatical at Microsoft. It was the day before I left. I gave a talk to the group which developed at the time what's now called C#. It didn't have a name yet at the time. It was this language without name. And so I showed them the picture on Java JVM modeling. I said, why don't you use this for developing your language? And it would be a big blow because you would have a precise semantics. You would have a manual where nobody can claim that it doesn't tell with precision what the language will do. And then I remember there was a person sitting there who was responsible for testing. He said, oh, gee, we can execute these things. That would be fantastic. We have 2,000 examples now of programs, and we already don't see the picture. That would help us to generate test cases and so on. Yes, sure, you can. And you have this mechanism to execute them and the debugger to make comparison and so on. And then there was a manual writer in the audience. He said, oh, that would be nice for writing good manuals. And I said, you see, Microsoft would be the company which comes out with precise manual. So they wanted to go for this, and the top management cut this off by saying, we are afraid this is a new method, too risky, we don't have time. And my answer was, you are losing more time by going this way, the traditional way, than applying this method. But I mean, that's how life is. What can you do?
So you talked about how Microsoft was able to ship the specification instead of the actual code and thereby protect the code IP while still being able to convince the European Union. So is the idea here that they use the Explorer as their argument for why this specification was actually something that the EU should trust? Because the counter-argument would have been, oh yes, you wrote a convenient spec that's convenient for what you want to demonstrate, but why should we believe the spec? So what was the story there behind?
Okay, I don't know the details, but here the story was, this was, so to speak, compelling, binding Microsoft by saying this is what we require implementations to do.
Whether they do it or not, this is what we promise that our implementations are required.
So if they behave following this specification, it will be compatible with Explorer.
So somebody else could then use the Explorer also to check this?
Yes.
I see. Interesting.
So that's the story Yuri told me. So.
okay, thank you. We should move on to the next story.
Okay.